All right, good morning everybody. So, meron ba tayong pending housekeeping matter? Mukhang wala naman, no? Tapos na ba yung deadline ng homework 6? Sorry, I forgot when did I set the deadline for that homework?
Today po ata yun, sir.
Today, right before midnight. Are you guys good with it or you want to extend it?
Ako po, i-rewrite ko na lang po sa, I think, pwede po bang i-type, sir?
Mag-write na. Sige, sure, yeah. So maybe just to be safe, I'll extend it until tomorrow, right before midnight. So it's gonna be the 20th. So yun na lang. Para magkaroon kayo ng konti pang time. And then as I said, I might, or actually, sige na nga, magko-commit na ako. I'll give you the last problem set for the course on Monday at around 8 a.m. It will be available in Canvas. The coverage will be modules 4 and 5 or units 4 and 5, differentiation and integration. But we will still have some things to cover next week. Ibibigay ko lang siya ng mas maaga para masimulan nyo na yung mga items tungkol dun sa derivatives at saka dun sa section 5.1 and possibly dun sa matatapos natin today para hindi na siya kasabay nung mga iba nyo pang problem set sa ibang subjects. Ano? But don't worry, the deadline would be on the last day of classes, June 9th. Okay? So para ilang linggo yon? Swerte nyo 1, 2, 3. So karoon ng mga 3 linggo para tapusin yung problem set. So I hope that's okay. Yun na rin lang yung kaunti kong may tutulong para medyo mapagaan yung trabaho nyo ngayong patapos na yung semestre. And then we'll have a final exam during the day of, ang deadline niya ay kung kailan yung final exams natin scheduled by the registrar. So try to submit any missing requirement that you have. I will accept them. Just put your explanation. And ba, meron pa kayong homework 1 or homework 2. Actually, super tagal na nga nun, no? So basta kung meron pa kayong mga naiwan na requirements, make sure to submit it siguro until June 9th. And then in your submission email, ilagay niyo yung explanation kung bakit. And then I'll decide. Depende kung anong deduction yung ibibigay ko sa inyo no, for the late submission. I might not give you a deduction if, number 1, the deadline is not too long from when you submitted it. And number 2, kapag okay naman yung reason. I mean, the reason is valid, okay lang. Pero kapag masyado ng malayo and your reason is possibly, sir, marami po akong problem set na nagsabay-sabay, I might give you little deductions. So, yun yung dalawang factors sa titingnan ko. Gaano nakatagal yung deadline, and number 2 ay yung reason. But sayang naman kung hindi kayo mag-attempt na magpasa. But I hope to get all of your works before June 9th because anything beyond June 9th, I will not feel obligated to grade it for the final grade. So pag magpapasa kayo ng something after June 9, itatamba ko lang yan sa email ko. Babalikan ko siya pag natapos ko na lahat ng mga, checkan lahat ng mga up-to-date submissions. So if you will fail to submit everything by June 9th, so malamang zero ko na kayo unless magsasabi kayo na may isa-submit pa kayo. And then there's no guarantee that I can grade that before the final, before the deadline for the final grades. If I get a submission from you between the final day of classes and a couple of days before the submission of grades or the deadline for the submission of grades, then I might give you an incomplete. Tapos antayin ko na lang yung completion period because I also have lots of things to grade ngayong patapos na yung SEM. So yung mga late submissions, nasa last priority ko na. Pero para mapasama kayo sa priority, submit it before June 9. Anything submitted after June 9 will be on the back burner and there is no guarantee that I'll be able to grade them. Pag nakita ko, si David nag-submit after June 9, ano na yun? Malamang ay, pag hindi ko na-checkan yung mga sinubmits mo, incomplete ka na. So, yun yung mangyayari. Tapos, hassle pa, ano pa kayo ng completion form for next semester. Pero sayang din naman yung grade kung kaya namang i-fill in. So yun na lang din yung chance na ibibigay ko sa inyo. Alright, so I think that's it for our housekeeping matters. So punta na tayo ngayon sa second section ng Unit 5. And it's about integrability criteria. So probably I'll change the title in the next iteration, plural na. Kasi marami tayo ngayong makikita na necessary and or sufficient conditions para sa integrability ng isang function. Nakita lang natin last time yung definition ng integrability. Ang isang function ay integrable kapag yung lower at saka upper Riemann integral ay naging equal, meaning the infimum of the upper Riemann sums and the supremum of the lower Riemann sums are equal to each other. And we said that's very difficult because you need to take the infimum and the supremum all throughout all possible partition inducers of the interval under consideration. So it's really quite a work to use the definition in order to show Riemann integrability. So kaya ngayon sa section na to, titingnan natin ano kaya yung mga mas madaling criteria. Number one, para masabi kung integrable ang isang function. At pangalawa, para masabi na ano yung value ng integral ng function na yon over the interval AB. Okay? And I think we had a couple of criteria last time. Tama nga ba? Meron na tayong pinrove na theorem about integrability. Ay, mukhang wala pa. Ngayon pa nga lang natin sila gagawin. Some sufficient conditions ay makikita rin natin ngayon. Okay, so let's start with Theorem 5.1, which is what we call the Integrability Criterion. So let's see what's the conditions here are. So we need to assume that f is a bounded function na integrable siya sa si f ay bounded function sa closed interval AB. Then we say that f is integrable or f is Riemann integrable if and only if sa kahit anong epsilon greater than 0, there exists a partition P of AB such that the upper Riemann sum and the lower Riemann sum of f with respect to those to that partition inducer are arbitrarily close to each other. So ang sinasabi ng Theorem 5.1, itong integrability criterion, integrable lang isang function pag pwede tayong makahanap ng partition inducer ng interval A, B na magiging napakamalapit na ng upper at saka lower Riemann sum nila sa isa't isa. In fact, whenever we choose epsilon greater than 0, however small it is, there's always a partition inducer na within epsilon distance yung upper at saka yung lower Riemann sum. Actually, you might think na, sir, obvious naman yan kasi gusto nga natin maging equal yung upper at saka yung lower Riemann sum. Yung infimum nito at saka yung supremum nito, gusto natin maging equal sa isa't isa. Remember, we are making them meet in the middle. So ito lang integrability criterion, parang ino-operationalize niya lang yung konsepto na gusto natin yung merong mga partitions na super lapit na ng upper Riemann sum at saka lower Riemann sum sa isa't isa. Okay? And the beauty about Theorem 5.1 ay meron tayong analytic way. So mag-i-issue siya ng challenge na epsilon, magbibigay tayo or maghahanap tayo ng partition inducer ng closed interval AB such that we have this epsilon inequality. And then by now, I guess you are now used to finding such responses sa mga challenge na epsilon. Ilang beses natin yung ginawa, limits, uniform continuity, what else? And all of the other previous topics. So let's try to prove it. It's a biconditional statement. So dalawang parte yung proof. Una, let's do the forward implication. Una, i-assume, actually, ito pala yung baliktad. Dapat ito ay backward implication muna. Alright. So, unahin natin yung pabaliktad. So, isusuppose ko na I can always find a partition inducer such that the upper and the lower Riemann sum are arbitrarily close to each other. Okay? Ang gusto kong ipakita ngayon, si f ay integrable. Alright? So, okay, let's see how that is done. inuna to kasi mas madali. Usually pag nagpo-prove tayo ng if and only if, inuuna natin yung mas madaling implication. So it turns out here, mukhang mas madali yung implication na yung pangalawang statement implying the first statement. Okay. Now let's see. Well, we will use the following facts. Yung upper Riemann sum, remember this is the infimum ng mga upper sums. So this guy is a lower bound para sa lahat ng mga upper Riemann sums. Hence this inequality. On the other hand, by definition, the lower Riemann integral is the supremum of the lower sums. Therefore, in the first place, it is an upper bound for all of the lower sums. So, sana tandaan nyo na yung dalawang inequalities na yan. And then, moreover, we know that okay. So, alam natin itong dalawang inequalities na to. Tapos, itong si U, papalitan ko to ng something na mas maliit, right? I will replace this by something smaller. Kasi papalitan ko siya nito. So, ito ay smaller. So, I mean, if I will keep this guy, i-keep ko siya. Pero ito, papalitan ko ng something na mas maliit. So the sum of this minus this guy will be smaller. Mas liliit. Kasi pinalitan ko yung minuend ng something na mas maliit. Moreover, I will also change the subtrahend by something that is larger. So nagma-minus ako ngayon ng mas malaking quantity. So that means if I replace this by something smaller and the and the subtrahend by something larger, then I will have a smaller number than this guy. So the difference between the upper Riemann sum and the lower Riemann sum will be smaller than the upper Riemann integral and the lower Riemann integral will be smaller than the difference between the upper sum and the lower sum. Yung upper minus lower sum ay mas maliit sa epsilon, so this difference will be less than epsilon. All right? And actually, not just that, we have proven last time na ang upper Riemann integral ay laging mas malaki sa lower Riemann integral. So actually, we can impose equality to an additional inequality over here. Tama? Na-prove natin na ang upper Riemann integral ay laging mas malaki sa lower Riemann integral. So I can put this inequality over here. And then, we can go back and stroll down memory lane para balikan sa Unit 1. Meron dong isang lemma na nagsasabi na kapag meron kang isang non-negative number, which we do have here, this is non-negative, na laging mas maliit sa kahit anong epsilon greater than 0, then we are left with no choice but to conclude that this guy is equal to 0. Nakalimutan ko yung number, pero tandaan nyo ba yun? Pag meron ka non-negative number na mas maliit sa lahat ng positive epsilons, yung real number na yun dapat ay 0. Wala nang ibang number na mas maliit sa lahat ng positive real numbers except kay 0. Of course, pati yung mga negatives. Pero wala nang non-negative real number na mas maliit sa lahat ng positive real numbers except kay 0. Okay? So that's why we will be forced to conclude that this guy must be equal to 0. So the upper and the lower Riemann integrals are equal to each other. Therefore, f is integrable on the closed interval AB. Okay? Tapos yung pakabila, it will require a little more work. So ang assumption naman natin dito, ito naman yung forward. Ang assumption natin dito ay si f ay integrable. Tapos gusto nating ipakita na pag binigyan tayo ng epsilon greater than 0, makakahanap ako ng isang partition inducer such that the upper Riemann sum minus the lower Riemann sum will be less than epsilon. Okay? So yun yung hanapin natin ngayon. Now, we know that f is integrable by assumption, so therefore the lower and the upper Riemann integrals are equal. Okay? Tapos gagamitin ko ngayon yung property ng infimum at supremum. So for any epsilon greater than 0, kung matatandaan nyo yung characterization ng supremum at infimum, okay? Dahil si upper Riemann integral ay ang infimum ng mga upper sums. So therefore, there exists a partition P1. Actually, ang mangyayari doon ay, dahil ito ay infimum, siya yung greatest lower bound, magdagdag lang ako sa kanya ng kahit anong positive number, hindi na siya lower bound. Tama ba sinabi ko kanina? This is the infimum. So this is the greatest lower bound. If I add something to it, a positive number to it, however small, it will not become a lower bound anymore. Because this guy is the greatest, pag nagdagdag pa ako sa kanya ng kahit katiting, hindi na siya magiging lower bound. So that's why we can find a partition inducer P1 of AB such that the upper sum of F with respect to P1 ay mas maliit na doon sa upper Riemann integral plus epsilon over 2. Alright? Tapos ganun din yung gagawin ko sa lower Riemann integral. Sa lower Riemann sum. Mukhang meron ditong correction. Tingnan natin. Well, recall that this is the supremum. So this is the least upper bound. Ito na yung least upper bound. Least upper bound. Okay. So pag nag-minus ako sa kanya ng kahit anong positive number, however small, hindi na to magiging lower bound. Hindi na siya magiging upper bound. Tama ba? Yan yung epekto ng pagiging bagong gising ngayon, no? So ulit, ito yung supremum ng mga lower sums. Supremum. So it is the least upper bound ng mga lower sums. Okay? So pag nag-minus ako sa kanya ng kaunti, hindi na siya magiging upper bound. So therefore, there will exist a partition inducer P2 of the closed interval AB such that that lower sum will be greater than the LUB minus a positive number. All right? Kasi hindi na nga ito pwedeng maging, ito ay hindi na pwedeng maging upper bound. So hindi na siya pwedeng maging upper bound, so meron ng isang lower sum na mas malaki kesa sa kanya. Agree ba? Or malabo? Okay lang? Makikita nyo, gamit na gamit natin yung mga properties ng mga infimum, supremum, ano? Okay, so we have now resolved that. So tingnan natin yung U minus L. Okay, U minus L. So it's going to be this guy minus this guy. Okay. Okay. So tingnan natin kung ano yung mangyayari. So si U ay yung minuend. Si U yung minuend. Okay. So si U ay papalitan ko ng something na mas malaki sa kanya. Okay. So pinalitan ko siya ng mas malaki sa kanya. So mas lumaki yung minuend. Tapos itong subtrahend, pinalitan ko ng mas maliit sa kanya. So the minuend increased, the subtrahend decreased, so we will get a larger number. Okay? So kaya ito ay mas maliit sa guy na ito. Alright? Tapos pag sinimplify ko to, equal to kay epsilon. Right? So ito na sana yung gusto nating ipakita. Kaya lang ang nandun nga pala sa theorem, dapat ay parehas yung partition inducer na ginamit. Okay? Kaya lang dito sa meron tayo, magkaiba yung partition inducer natin ginamit. We have the right inequality. We want the upper and the lower Riemann sum to be less than epsilon. But the theorem says dapat parehas yung partition inducer. Ito ang partition inducer ay P1, ito ang partition inducer ay P2, so hindi pa tayo tapos. So kailangan ko makahanap ng isang common partition inducer na yung upper at saka yung lower Riemann sum ay less than pa rin kesa kay epsilon. Pero ngayon, gagamitin ko yung konsepto ng refinement. I will define P sub epsilon to be the union of P1 union P2. So that means si P epsilon ay refinement ni P1 at refinement din ni P2. And remember what the effect of refining a partition inducer is with respect to the upper and the lower Riemann sums. All right? So remember, kapag gumamit ka ng isang refinement ng isang partition inducer, mas lumiliit yung upper Riemann sum. So if I will replace this guy by the upper sum relative to the refined partition, mas maliit na. So ito, napalitan ng mas maliit na partition inducer. Ng mas maliit na upper Riemann sum. Tapos yung subtrahend dito ay lower sum. Pero pag ni-refine ko yung partition inducer, mas lumalaki yung lower sum, right? So if I will replace this by the lower sum relative to a refined partition, mas lumiliit yung difference. All right? Because the minuend decrease, the subtrahend increase, so the difference will be smaller than the original difference. But we know that the original difference is less than epsilon, therefore this guy is less than epsilon. Now, what we have shown here, bigyan tayo ng kahit anong epsilon greater than 0, we can always supply a partition inducer, in particular, the partition inducer P sub epsilon, so that this guy will be less than epsilon. And that ends our proof. Okay? Any questions? Okay pa naman? Medyo maraming dinaanan, no? Maraming tools na ginamit mula sa previous topics, but I hope unti-unti nyo nang naalala yung mga tools na yun, ano? Kasi they will always come in handy. Okay, so let's just illustrate it a bit. Pinakita lang dito na Riemann integrable ang constant function, but I think we already did it last time. Ang ginagawa lang natin dito ay tinatay ko na siya sa konsepto ng limit kasi gusto natin yung difference between the upper and the lower Riemann sums to be arbitrarily close to 0, right? So ganun yung titingnan natin. So tingnan nyo sa example 5.6, medyo ginagamitan ko na siya ng limit argument. So rito, magko-consider ako ng isang partition inducer P na ang laman niya ay 0, 1 over n, 2 over n minus 1 over n hanggang makarating kay 1. So this is a partition inducer of the closed interval 0, 1. Tapos instead na kunin ko yung upper Riemann sum at saka lower Riemann sum separately, what I will now analyze would be the difference between the upper and the lower Riemann sum. And I will analyze this and see, kaya ko ba itong gawing arbitrarily close sa isa't isa? Okay? Kasi pag napakita ko na I can make this as close to 0 as possible, then we're done. That would be Riemann integrable. Okay? So, pero dito specific nga yung family of partitioning na ginamit ko, ano? Pero that would come in handy later. So let's calculate the upper minus the lower Riemann sum. Using the formulas for these sums, it's going to be the maximum over the ith interval minus the minimum over the ith interval times the length of the subinterval. Okay? So yun yung formula ng upper minus lower sum. Tapos, identity function lang yung ginagamit natin. So yung maximum lagi ay yung right endpoint ng interval. So ang mga subintervals natin dito, ang itsura ay x sub I minus 1 hanggang x sub I, right? So capital M sub I would be the right endpoint. That would be the largest function value all throughout this subinterval. So we got little xi here. The minimum would be x sub I minus 1. So siya yung lalabas rito. And then we have the step size here, yung length ng ith subinterval. But this guy is also the length of this interval, right? So that's also a delta x sub I. So basically here, this is the summation of the squares of the lengths of the subintervals. But look at how we define the partition inducer. Here we considered a uniform step size, right? So magkakasing layo yung mga partition inducers mula sa isa't isa. Okay? So in fact, the length of each of the subintervals is 1 over n. So therefore, this guy inside the summation will be 1 over n squared. So we are getting the sum ng n na 1 over n squared. Okay? So ibig sabihin, ang sum lang nito ay 1 over n. And the idea here is we can choose, whenever we are given an epsilon greater than 0, we can always find a large enough n such that 1 over n will be less than epsilon. Do you guys remember what that property is called? na kapag may given na sa akin na epsilon greater than 0, lagi akong may mahanap na natural number little n, no, ang 1 over little n ay mas maliit dun sa epsilon na yon. Tandaan niyo yung tawag. Anong property nga yun, guys? Tama si David. Thank you, David. That's perfect. It's the Archimedean Principle. So by the Archimedean property, kaya kong makapili ng little n such that this guy will be less than any given epsilon. So that tells us there is a partition inducer of this form that can make this difference very, very close to 0. And therefore, by the integrability criterion, f is integrable on the closed interval 0, 1. Okay? All right. Now let's move on and tingnan natin, tumingin tayo ng ilan pa mga sufficient conditions para sa Riemann integrability. So we have Theorem 5.2. Ang premise lang natin dito, dapat si f ay bounded on the closed interval AB. Now kapag ka siya ay bounded and at the same time continuous on the closed interval AB, so another typo here, this should be AB. Okay. Then si f ay automatically integrable sa AB. So continuity implies integrability, but this is something that you already know from Math 36, right? Kasi dinefine nga natin doon ng integral para sa mga continuous functions, all right? So na-formalize lang natin siya dito na kapag ka ikaw ay bounded and continuous, automatic ikaw ay integrable sa closed interval AB. And then there's another sufficient condition, boundedness plus monotonicity is sufficient para ma-conclude na integrable ang isang function. And that's what we'll prove in the following lines. Okay. Assume na natin na si f ay bounded. Tapos part A, ang assumption, si f ay continuous. Okay. So si f ay continuous sa closed interval AB. Si closed interval AB ay compact. So therefore, by one of the theorems before, kapag ang isang function na continuous sa isang compact set, siya ay uniformly continuous dun sa compact set na yon. May pangalan ba tayo para sa theorem na yon? Hindi ko matandaan kung ito yung Fermat's theorem, though hindi ko yata binanggit sa inyo yung pangalan na Fermat's theorem. But I need to check. But I hope you remember, ng isang continuous function, as long as it is, if a function is continuous on a compact set, then it is uniformly continuous on that compact set. Okay. Dahil siya uniformly continuous sa compact set closed interval AB, then by definition, pag binigyan ka ng epsilon greater than 0, laging may mag-exist na delta greater than 0 such that whenever x and y are within delta units away from each other, then f of x minus f of y can be made arbitrarily close to each other. In particular, close within epsilon over b minus a units away. Okay? So, dun sa uniform continuity, epsilon sana to. Kaya lang, matatandaan nyo, usual trick natin, no? Kaya nating mag-introduce ng kahit anong multiplier dun sa epsilon. Kasi si epsilon ay arbitrary, tapos si arbitrary divided by a constant, arbitrary pa rin yung sagot. Alright? So, pinili ko lang talaga na, okay, pipiliin ko yung delta na yung f of x minus f of y ay within epsilon over b minus a units away. Okay. And then dahil si f, aside from being continuous, ay assumed to be bounded, then para mapakita na si f ay integrable, pwede natin gamitan yung Theorem 5.1, yung Integrability Criterion natin, na sinasabi na kailangan lang nating magpakita na may nag-exist na partition inducer P such that this is true. Okay? Yung upper Riemann sum minus lower Riemann sum ay less than epsilon. Well, how will we do that? Well, ang idea rito ay piliin ko daw yung partition inducer P such that the length of each of the subintervals ay less than the delta that was imposed over here. Okay? So meron na tayong specific delta na nagmula dun sa challenge na epsilon mula dun sa uniform continuity ni F. So sinasabi ngayon sa proof, may delta ka, yan yung gawin kong maximum or gawin ko siyang upper bound para sa lengths ng bawat subinterval doon sa partition. So in other words, I'm going to choose a partition inducer P such that the length of each of the subintervals ay hindi tataas ng delta. And you can guess why I want that to happen. I want that to happen so that yung mga x's sa loob ng ith subinterval ay masasatisfy yung x minus y less than delta. Okay? Now, ano yung pwede nating sabihin? Okay, si f ay continuous dun sa buong closed interval. So siya ay continuous din sa bawat subinterval. Tapos, by Weierstrass's theorem o yung extreme value theorem, dahil si f ay continuous sa compact set na to, then it will attain its maximum and minimum at that interval. So that means there exists an x sub capital M sub I and an x sub little m sub I such that maximum yung function value dito, minimum yung function value dito over the ith subinterval. Okay? So what do we have now? Well, remember, sinabi natin na yung haba ng bawat subinterval ay hindi lalampas ng delta. Pero ngayon, si x sub mi at saka si x sub mi ay nasa interval i na ang haba ay hindi lalampas ng delta. So totoo ito. So magkikick in itong inequality na to para sa function values ng dalawang x's na ito. So in particular, So, burahin ko na nga to. Hindi, sige, keep ko na to. So, ito yung maximum sa ith subinterval. Ito yung minimum sa ith subinterval. Pero, wala na to dapat. Tapos ito ay pwede kong isulat na f of x sub m sub I. Ito ay pwede kong isulat na f of x sub little m sub I. And then dahil yung mga x's dito ay nasasatisfy yung delta inequality sa uniform continuity, so that means the epsilon inequality dun sa uniform continuity dapat nag-hold din. So this guy, which is basically your supremum minus the infimum on the ith subinterval, is less than b, or has difference that is less than epsilon over b minus a. Tapos ngayon makikita nyo na kung bakit epsilon over b minus a yung pinili ko. Kasi ngayon, kukomputin ko yung upper minus lower Riemann sum with respect to the partition inducer P na dinefine natin dito. Alright? So ang formula para sa upper minus lower sum ay eto. Kaya lang alam ko na itong difference na to coming from here ay laging mas maliit sa epsilon over b minus a. So this guy is bounded above by epsilon over b minus a, which doesn't depend on I. So yung bound na yun ay lalabas ng summation, kaya ito nandito. Right? And then ito na lang yung kailangan natin i-compute. However, this is the summation of the lengths of each of the subintervals. But what do we have here is a partitioning of the closed interval AB. So the sum of each of the subintervals is equal to the length of the original interval AB. So therefore, this summation is just b minus a. And so finally, we have epsilon over b minus a times b minus a, product being equal to epsilon. And now we have shown that there exists a partition inducer P such that this difference is less than epsilon. So by the integrability criteria, integrable ang isang continuous function. Ang daming pinagdaanan, no? Oh, as long as it is bounded. First part pa lang pala to. Wala pang end of proof. Oh, thank you, David. Theorem 3.9 daw yung preservation of compact sets nga ba yun, David? All right, let's questions with that. Pwede na tayong tumuloy sa next part ng proof. Ito naman ay kapag si f ay monotonic. If f is monotonic and bounded, then ibig sabihin siya daw ay integrable na. Tingnan natin kung bakit. All right? So, without loss of generality, let's assume that f is increasing. A similar argument can be written if f is decreasing. Monotonic kasi yung assumption, so it's either monotonically increasing or monotonically decreasing. So let's just write the proof for monotonically increasing functions. Okay. Kung siya ay monotonic increasing, then okay, kung siya ay monotonic increasing, then the minimum or the what do you call this, the infimum of the function values ay guaranteed to occur at the left endpoint, right? So yung minimum ni f, siya ay na kay f of a. Kasi nga increasing siya. Pinakamababa yung function value nung pinakamababang x doon sa interval. And then on the other hand, yung maximum naman, maninirahan siya dun sa right endpoint kasi nga increasing yung function. Okay? Kung baliktad, kung si f ay decreasing, sa baliktad lang. Ito ay f of b, ito ay f of a. And I think the argument will still hold. Yun lang yung kailangan yung baguhin. Now, if little m is equal to m, meaning the maximum is equal to the minimum, then f is necessarily the constant function. Dahil constant function yan, na-prove na natin yan last time that f is integrable. Now, ang mas mahirap kapag ka si little m ay hindi equal kay capital M. Ibig sabihin, hindi na to constant function. Now, we only have one case for that. Mas maliit yung little m kaysa sa upper m kasi ito nga yung minimum, ito yung maximum. Now, kapag ka binigyan daw tayo ng epsilon, kasi gagamitin ko yung integrability criterion ulit. So, pagka binigyan tayo ng epsilon, mula dun sa challenge ng integrability criterion, pwede akong pumili ng isang partition inducer ng closed interval AB such that the lengths of the subintervals will not exceed epsilon over big M minus little m. So kasi existence lang naman yung hinihingi ng integrability criterion. So pag binigyan ako ng epsilon na challenge, sabihin ko, sige, ang pipiliin ko ay kahit anong partition inducer such that lahat ng subintervals sa partition na mabubuo ay may haba na hindi lalampas ng epsilon over m minus m. And this is the reason why I need to consider the first case, na si m ay equal kay capital M. Kasi pag si little m ay equal kay capital M, magsi-zero yung denominator, may butas yung proof. So kaya ito dinagdag dun sa unahan para assume na natin na hindi equal kay 0 yung denominator. And moreover, we know that the maximum here is greater than the minimum, so this guy is greater than 0 pa rin. So wala pa tayong problema so far. So gusto ko na lang ipakita na with this choice of partition inducer, the upper minus the lower Riemann sum will not exceed epsilon. All right? And then if we'll be able to do that, then by 5.1, we're done. F is integrable. Okay? So simplify. Okay, this guy, ito yung formula para sa kanya. Pero what do we know? Oh, we have bounded delta x by the way we chose the partition or the partition inducer P ay such that yung length ng bawat subinterval ay hindi lalampas ng epsilon over m minus m. This is independent of the summation index I. So lalabas siya sa harap ng summation. We'll get this. Okay? Now, we are now using the fact that m is, that f is increasing. So capital M sub I is equal to f of x sub I. Yung nasa kanan, yung minimum value, little m sub I, ay equal sa function value na nandun sa kaliwang endpoint kasi nga increasing si f. But this guy is bounded above by the maximum all throughout the entire interval AB. Meanwhile, the subtrahend is bounded below by the minimum all throughout the interval AB. So papalitan ko ngayon ito ng something larger, papalitan ko yung subtrahend ng something smaller, so I'll get a larger sum. So kaya medyo may mali ito, dapat ito ay less than dyan. Kasi nga ito ay mas maliit dito. Ito ay mas maliit dito. Ito ay mas maliit kesa dito. Ito ay mas malaki kesa dito. So I should get a larger number. Okay? Kasi ito yung dahilan kung bakit pinili ko yung length to be less than epsilon over m minus m. Kasi alam ko meron akong matitirang factor dyan na m minus m yung lalabas. Or actually, check that. Tama pala to. Ayan, nagets ko na kung bakit. Kasi pag in-expand ko to, siya ay f of x1 minus f of x sub 0. Okay? Plus, kapag kasi I ay 2, f of x2 minus f of x1. Plus, hanggang makarating ako sa I equals n, f of xn minus f of x sub n minus 1. Tapos magte-telescope ito, no? Kasi magkakaroon ako ng f of x1 minus f of x1, f of x2 makakancel ng f of x2, then itong minus f of x sub n minus 1 makakancel siya nung nandito, matitira lang ay f of xn minus f of x sub 0. Okay? Kaya magiging f of xn, which is f of b, which is capital M, kasi ito ay f of x sub 0, which is f of a, which is little m. So, ganun yung nangyari. Maka-cancel ito, maka-cancel yan. Matitira si epsilon. At the end of the day, we have the upper Riemann sum minus the lower Riemann sum less than epsilon for the specific partition inducer P that we have chosen. And so by the integrability criterion, yes, any monotonic increasing function is integrable. The same thing goes for monotonically decreasing function, because I could have just switched the places of A and B dito sa definition ng little m at saka capital M. All right? All good? Medyo nahasa tayo ngayon na mag-work with inequalities. Yes, David, you have a question?
So, question po, sir. Final na po yung mga yung equals tsaka less than signs po dyan.
Yep. Meron ka pa ba napansin na kailangan baguhin? I think tama na siya. Never mind the corrections I inserted kanina.
Pwede po
Or may na-miss ba?
Wala naman po, sir. Pwede po ba pa-explain bakit po larger yung pangatlo sa pangalawa po, sir?
Okay. Hold on. Eto ba?
Yes po.
Okay. Yeah. Nanggaling siya kasi wala ko ditong etong unang term, hindi ko yan binago. Ito ay equal dito. So, okay yan. Kasi yung capital M sabay, siya yung maximum sa ith subinterval. Yung little m sabay, siya yung minimum sa ith subinterval. Pero dahil increasing si f, alam natin na yung maximum magaganap dun sa right endpoint. Tapos yung minimum magaganap dun sa lower endpoint ng ith subinterval. So wala akong ginalaw dun sa unang factor. Tapos, naging less than to, gawa kasi yung delta x sub I ay laging mas maliit sa epsilon over m minus m. And that is by our choice of the partition inducer. Sinabi natin kanina na pag binigyan ako ng epsilon, ang pipiliin kong partition inducer ay kahit na anong partition inducer such that ang length ng bawat subinterval dun sa partition na in-induce niya ay hindi lalampas ng epsilon over m minus m. So basta nakakita ko ng delta x sub I, lagi yung mas maliit sa epsilon over m minus m. So this guy, mapapalitan to ng epsilon over m minus m, pero pag ginawa ko yung pagpapalit na yon, I'll get a larger number because I will essentially end up multiplying it by a larger number. So this is larger than the previous one. Tas dahil ito ay walang I dun sa expression, pwede siyang lumabas ng summation. Kaya ako nakuha ito. Tapos greater than siya kasi nga ito ay mas malaki dun sa pinalitan ko kanina. Alright? Does that make sense?
Apo, thank you, sir.
Alright. Okay, thank you, David. And with these two theorems, pwede na nating sabihin na, okay, yung x to the power n, kasi continuous siya. So siya ay integrable. Sin x, continuous, so integrable yan. E to the x, continuous, so integrable yan. Okay? Pwede mo ring sabihin, ito ay increasing. So ito ay integrable din. Now, e to the sin x is integrable because it is the composition of two continuous functions. So continuous circle, continuous ay continuous, continuous at saka bounded implies integrable sila sa closed interval AB. And then moreover, this discontinuous function, yung floor function, alam natin discontinuous yan sa bawat isang integer. Na-prove na natin yan dati. Pero dahil increasing yan, so by the previous theorem, siya ay integrable din. Okay? Now, medyo generic yung sufficient condition natin kanina. Sinabi natin na kapag ikaw ay continuous at bounded, so ibig sabihin ikaw ay automatically continuous. Pero kapag ikaw ay integrable, hindi nangangahulugan na ikaw kagad ay continuous. Katulad ng example natin kanina, yung kababanggit ko lang, yung floor function ay discontinuous, pero siya ay integrable. Okay? So, itong Theorem 5.3, magbibigay siya sa atin ng isang condition kung kailan i-allow niya yung mga discontinuous functions na maging integrable. Actually, Theorem 5.3 is telling us that if your function is continuous except for a finite number of points, then si fi integrable pa rin. So, ang sinasabi niya, okay lang na ikaw ay discontinuous sa finite number of points doon sa closed interval AB, papayagan ka pa rin namin. Hindi kailangan maging perfect yung isang function. I mean, perfect with respect to continuity. Kahit may maliliit kang faults, basta finite lang yung number of faults, so points of discontinuity, ikaw pa rin ay integrable. As long as sa other points on that closed interval, ikaw ay continuous pa rin. Okay? So, titingnan natin yung proof kung paano siya ginawa. So, ang idea rito ay, halimbawa meron akong closed interval AB. Tapos ipagpapalagay ko lang na, okay, discontinuous siya kay Z1, kay Z2, kay Z3, kay Z4, hanggang kay Zn. Meron ka lang finite points of discontinuity. Tapos gusto ko ipakita na continuous, na integrable pa rin si function f kahit na siya ay discontinuous sa mga c sub n's. Okay? Now, what I'll do is choose, I'll assume that we are given an epsilon greater than 0. Tapos, assumption nga rin pala dito ay bounded, so mag-apply yung integrability criterion. So, kaya magko-consider ako ngayon ng epsilon greater than 0. And then I want to show that the upper minus lower Riemann sum can be made so that they would be less, or their difference would be less than epsilon. Now, ang gagawin ko rito ay, kung given na si epsilon, okay, pipiliin ko si delta to be the minimum between these guys. Tapos sabihin nyo, out of this world naman yung choice ng delta. Minimum siya ng epsilon over 8 over mn. Where the hell did that come from? Makikita natin mamaya. And titingnan kayo mas maliit kasi sa c sub 1 minus a over 3, c sub 2 minus c sub 1 over 3, and so on. So by the way, dito in-assume nga pala natin na yung c sub I ay written in increasing order. Okay? So, kaya nandyan yan. Kaya positive lahat ng nandito sa loob ng pinagmi-minimum natin. Okay? Tapos si f ay bounded, so yung upper bound para sa function o para sa magnitude ng function value ni f, siya yung tatawagin capital M. Tapos si little n naman, si capital N naman, siya yung number ng points of discontinuity. Okay? So, ang idea ay bakit ko siya kukunin na yung delta dapat ay mas maliit sa epsilon over 8 minus epsilon over 8 times mn. Makita nyo mamaya kasi magkakaroon ng multiplication by something involving mn, gusto ko sila ay makancel. Okay? Tapos, bakit to kasama? Bakit kukunin ko pa yung minimum among these guys? Kasi yung numerators ng mga to, sila yung nagsasabi gaano kalayo yung isang point of discontinuity from either another point of discontinuity or dun sa endpoints. Tapos kukunin ko yung 1/3 noon. The very idea of including this in the battle for the choice for delta ay para ma-ensure na magkakaroon ako ng mga sub-intervals na hindi magko-contain ng more than one point of discontinuity, and makakabuo ako ng mga subintervals na walang point of discontinuity. Okay? Because with this choice of delta, sure ako na si C, wala nang ibang point of discontinuity dun sa delta neighborhood ni C sub 1. Kasi nga, ito si delta. Si delta dapat ay hindi lalampas ng Z2 minus Z1 all over 3. So itong distance na to, hindi siya lalampas ng 1/3 nung distance sa pagitan nitong dalawa. So sure ako, nakukulong ko yung bawat point of discontinuity sa isang open interval. Okay? Good so far? Maraming dadaan kasi itong proof na to. Okay, so I hope nakita niyo yung choice nung delta, no? So pinili ko yung delta so that nakukulong sila. Tapos, yung union ng mga to, ito yung tatawagin kong P0. So kukulayan ko na lang sila. Siguro kulayan ko ng yellow. Itong mga yellow intervals na yan, yung union nila, yan yung tatawagin kong P sub 0. Okay? So yun yung mga yellow intervals, yung mga P sub 0. And then tatawagin kong E sub i's, ito naman. Ito si E sub 1, ito si E sub 2, ito si E sub 3, ito si E sub 4, and so on. E sub 5. So kung mapapansin nyo, si F ay continuous sa bawat E sub I. Kasi yung A to Z sub 1 minus delta ay walang laman na point of discontinuity. Yung E2, which is from C sub 1 plus delta hanggang sa C sub 2 minus delta, ay walang laman na point of discontinuity. So continuous si F sa E sub 2, and so on. So parang dito nakabuo ako ng dalawang klase ng subintervals. Meron akong orange subintervals, yun yung mga E sub i's. Tapos meron akong kung saan continuous yung function f. Tapos meron akong yellow subintervals kung saan may laman sila na isang point of discontinuity. Alright? Tapos, okay. Then si f ay continuous sa bawat isang E sub I. So ibig sabihin si f ay integrable dito. F is integrable here. Okay. So ibig sabihin yung upper Riemann integral, yung upper Riemann sum relative to this partition, paano kaya siya isusulat? Let's see. Okay. Tawagin ko na lang siyang P sub I. Alright. So si P sub I ay isang partition inducer ng interval E sub I. Right? So dahil ulit, si F ay continuous sa interval E sub 1. So ibig sabihin, by the integrability criterion, meron akong partition inducer Pi ni E sub 1, or sabihin ko na lang itong P sub 1, partition inducer P sub 1 ni E sub 1 that I can make the upper Riemann sum minus the lower Riemann sum arbitrarily close to each other and say this is less than epsilon over 2 times n plus 1. Kasi nga pwede akong pumili ng kahit anong multiple ni epsilon na magiging upper bound noon. So ganun din yung mangyari kay E2. Si F ay continuous kay E2. So ibig sabihin siya ay makakakita ako ng partition inducer ni E2, say P2, such that the upper Riemann sum relative to P2 minus the lower Riemann sum relative to P2 ay less than epsilon over 2 times n plus 1. Again, so nanggaling yung 2 times n plus 1, makikita natin later. Pero yun yung idea. Okay? Tapos, hindi natin magagawa ito doon sa mga yellow intervals kasi hindi integrable si f doon sa mga yellow integrals. But what do we know about them is Actually, ang alam lang natin dito ay ang haba nitong subintervals na to ay what? Ay 2 delta units. Tama ba? Delta minus delta. Yeah, it's gonna be 2 delta units. Yun lang yung alam natin doon. Yung haba nila ay 2 delta units. Okay? But delta, we know, was chosen to be the minimum between these guys. Okay? Tapos ngayon, bubuuin ko na yung argument. Right? So, tatawagin ko ngayon na ito si t sub 0. Tapos ito si t sub 1. Si t sub 1 ay si c sub 1 minus delta. Tapos ito, kukunin ko yung mga boundary points. Tatawagin ko silang t sub i's. Si c sub 1 plus delta, siya si t sub 2. Si c sub 2 minus delta, siya si t sub 3. Tapos ito ay si t sub 4, and so on. Hanggang makuha ko to si t sub, say, n. Alright? So meron ako ngayong partition inducer. Partition inducer T0, T1, T2, T3 hanggang kay T sub n. Tapos sila lamang yung mga boundary points. Sila yung mga C sub I minus at saka plus delta at saka si A at saka si B. So isa siyang partition inducer ni A. Tapos kukunin ko ano yung itsura ng upper Riemann sum minus lower Riemann sum relative doon sa partition inducer P comprised of T0 hanggang kay Tn. Okay? Pero alam na natin na bawat isang subinterval kay P, okay, ay either isang orange interval o isang yellow interval. Okay? So, yun yung nangyari dito. Hinati ko siya sa dalawang classes. Dito, pag plusin ko lang yung Riemann yung difference ng upper at saka lower Riemann sum mula dun sa mga yellow intervals kung saan may discontinuity. Tapos dito naman sa pangalawang sum, kinukuha ko yung summation ng mga upper at saka lower Riemann integral, upper at saka lower Riemann sum dun sa mga orange subintervals. Okay? Tapos pag sinum ko ito, makukuha ko yung total upper minus lower Riemann sum. Okay? Now, unahin natin to. Ito ay dun sa mga orange intervals. So alam natin ito ay equal dun sa upper minus lower Riemann sum sa bawat subinterval. Okay? Tapos alam na natin yon na ito, na-compute na natin yan, bawat isang yan ay hindi lalampas ng epsilon over 2 sub n plus 1. Remember? Pinili ko yung p sub I to be no more than epsilon over 2 times n plus 1. Kaya siya lumabas dyan. Tapos ito ay independent ng I, so lalabas siya dyan. So magiging ang sum niya lang ay epsilon over 2 times n plus 1. Tapos there would be n plus 1 of them. Alright, maka-cancel yung n plus 1. Kaya pala nag-multiply ako ng n plus 1 dun sa denominator. Natira lamang ay epsilon over 2. Okay? Okay, we're halfway done. Puntahan naman natin itong kabila. Ito naman ay nanggagaling dun sa mga points of, dun sa mga intervals na yellow na may mga points of discontinuity. Alright? Now, unahin natin to. Mas madali kasi to. Ti minus t sub I plus 1. This is 2 delta, right? Kasi ito yung haba ng bawat sub-interval na yellow. So, 2 delta yan. There you go, 2 delta. And then, capital M sub I minus little m sub I. Ito yung maximum sa ith subinterval. Ito yung minimum dun sa isang subinterval. Pero ito ay mas maliit kaysa sa maximum sa buong interval. Tapos ito ay mas maliit sa negative. Actually, dito. Ulit. Ito ay mas maliit sa absolute value ng upper bound kasi sabi natin si M ay bounded. In particular, we said that M is, or the absolute value of F is bounded above by M. So, ibig sabihin, ito ay hindi bababa sa absolute value of M. Tapos ito naman ay hindi tataas kay absolute value of M. So meaning, this difference ay hindi lalampas ng 2 times M. Okay? Kasi nga, remember, ang absolute value ng f of x ay less than M. So ibig sabihin, ang f of x ay hindi lalampas ng negative m papunta kay m. So pagka nag-subtract ako ng dalawang numbers na nasa pagitan ni minus m at saka ni capital M, yung difference nila ay hindi pwedeng lumampas ng 2m. Tapos, okay, 2m, tapos 2 delta, wala silang I, lalabas silang dalawa nung, lalabas yung product na yon sa summation. Tapos summation lamang to ng 1. There would be n of them. So the simplified version for this guy is 4m delta times n. Tapos dito na papasok yung choice natin for delta. Sabi natin si delta ay hindi lalampas ng 8, ano ang sinabi natin? mn over 8? Tama ba? Epsilon over 8mn. So ito ay hindi lalampas ng epsilon over 8mn. May mn dyan. Cancelled yun. May 4 sa taas, may 8 sa baba. Epsilon over 2 yung matitira. Epsilon over 2 plus epsilon over 2 equals epsilon. So what we have shown here is that we have devised a partition inducer P such that the upper minus lower Riemann sum ay less than epsilon. So by the integrability criterion, ibig sabihin ay integrable yung function f. So sinasabi niya, okay, pwede ka maging discontinuous pero pag finite lamang, yung number of discontinuities mo, hindi ka na, ikaw ay integrable pa rin. Alright? Pero ginawa niyo na to sa 36, no? Ginawa niyo nga lang ng 36 ay kinonsider nyo yung, hinati nyo yung integrals. Alright? Meron kang definite integral A, B, tapos pag may isang point of discontinuity doon sa interval na yon, hatiin mo lang yung integral sa dalawang parts. Integral mula dun sa integral dun sa interval sa kaliwa ng point of discontinuity at integral sa kanan ng point of discontinuity. You add the two integrals, then you get the integral for the entire interval. Parang ganito rin yung ginawa natin dito. Pinaghiwa-hiwalay natin yung mga may points of discontinuity. Okay? All right. Questions? Medyo nakakatuwa yung proof, pero parang hirap niyang isipin pag tayo lang yung magsusulat ng proof, ano? Okay. Siguro last two results, mag 12:15 na naman. Okay. Now, i-characterize lang natin, ano, kasi ang alam lang natin so far, posible kang maging integrable kung ikaw ay discontinuous. And the previous theorem tells us na kapag ka finite lamang yung points of discontinuity mo, then ikaw ay automatically integrable na. Now, we might ask, ano na yung pinaka-posible o pinakamalalang klase ng discontinuity na pwede ka pa rin maging integrable? Kasi kapag ka finite lang yung number of points of discontinuity mo, posible ka pang maging integrable. Pero how far can we push it, no? Yung pagiging discontinuous para ma-maintain pa rin na ikaw ay integrable. Ang sagot doon ay yung Lebesgue criterion for Riemann integrability. Okay. Pero para masabi, kailangan ko munang i-define ano yung set of measure 0. Okay? Ang isang set ay tatawagin nating set of measure 0. Ibig sabihin siya yung set na ang sukat niya ay 0 kapag ka sa kahit na nung epsilon greater than 0, makakabuo ako ng union ng mga countable intervals. Union ng isang countable number of open intervals such that the union will cover the set A. Ibig sabihin, kaya kong matakluban si set A ng union ng mga open intervals na yon. And the total lengths of the open intervals must not exceed epsilon. So ang measure ng isang set ay 0 kapag ka makakahanap ako ng isang countable family na mga open intervals na yung union ng mga open intervals na yon ay kaya niyang matakpan yung set A, pero dapat yung sum ng mga lengths nung mga open intervals na yon na pinangko-cover ko ay hindi lalampas ng epsilon. And you should be able to do this for all epsilon greater than 0. So ibig sabihin, ang isang set ay magkakaroon ng measure 0 kapag kaya ko siyang takluban ng napakaliliit na open intervals. There is a countable family of very, very small open intervals that can cover the set A. So, halimbawa, kapag meron tayong finite set, A1 to AN, okay? Pag binigyan ako ng epsilon greater than 0, kaya ko pa rin makabuo ng mga open intervals na makakapag-cover kay set A, pero yung sum ng lengths ng mga open intervals ay hindi lalampas ng epsilon. Kasi yun yung challenge dito. Bibigyan kita ng budget na epsilon. Dapat bumuo ka ng mga open intervals na ang total length ay hindi lalampas ng epsilon. So nagbabudget ka ngayon epsilon, yung total lengths ng mga subintervals na gagamitin ko. Kaya ko bang makakuha ng mga open intervals na magko-cover kay set A na nandun ako sa budget ko para sa lengths ng total, para sa total lengths ng mga open intervals na gagamitin ko. Okay? So kapag finite yung set A, meron siyang capital N elements, kaya nating bumuo ng open intervals na ganito yung itsura. AN minus epsilon over 2n, comma AN plus epsilon over 2n. Clearly, bawat isang A sub n na nakay A ay nasa isa dun sa mga open intervals. Kasi ang ginawa mo lang naman dito, meron kang A1, A2, A3, A4, and so on. Binuo mo lang to. Ito yung AN minus epsilon over 2n. Ito yung A2 minus epsilon over 2n, comma A sub 2 plus epsilon over 2n. So ito ay epsilon over 2n. Tas ito, tas ito, tas ito. Right? So nako-cover nung union ng mga intervals na to yung set A. Kasi bawat isang element ni set A ay nasa loob ng isa sa mga open intervals na kinonsider natin. Tapos, gaano ba kahaba bawat isang subintervals? Bawat isang open interval. Bawat isang open interval, ang haba niya ay epsilon over capital N. Pag sinum ko yung haba ng bawat interval na yun ay magiging epsilon over N times N lamang. So nandun ako sa budget ko na hindi lumampas ng epsilon yung total length nung mga open intervals na kinonsider ko. So that means any finite set has measure 0. Okay. Tapos, kapag meron ka namang countable set, measure 0 pa rin yun. Pag meron kang countable set, kahit infinite yung laman niya, basta countable, alright? Ibig sabihin, may discrete way of listing them down, right? Hindi ka nga lang natatapos pagsusulat, pero countable siya. Kaya mo siyang bilangin, hindi ka nga lang matatapos magbilang. Yun yung ibig sabihin ng countable in layman's terms. Ano? Kung countable naman yung set mo, eto naman yung family ng mga open intervals na gagamitin natin. Ang length ng bawat isang open interval na ipang-cover natin ay epsilon over 2n plus 1. 2 to the power n plus 1. Clearly, these open intervals will cover the set E. Kasi sa bawat isang element ni E ay mapapalagay as a center ng isa dun sa mga open intervals na yan. Tapos, bawat isang open interval na ganito yung itsura, ang length niya ay epsilon over 2 to the power n plus 1. So, pag sinuma-total ko yung mga lengths ng mga intervals na yon, kaya lang countably infinite din ito, no? Kasi countably infinite si E. Tapos sabi natin, bawat isang element ni E dapat center ng isa dun sa mga open intervals. Pumapayag naman tayo na countable yung number of open intervals, basta wag lang lalampas ng epsilon yung total lengths nila. So tingnan ko, ano ngayon yung sum ng mga lengths? Kunin ko lang yung summation ng mga lengths ng bawat intervals. But we have noted earlier that each open interval will have length epsilon over 2 to the n plus 1. Tapos ito ay geometric series. Geometric series ito ng summation lamang ay epsilon over 2. Sobra pa tayo sa budget natin na epsilon. Since nakabuo tayo ng isang open cover or isang family of open intervals that can cover the set E, then the set E is what you call this, is of measure 0. So ngayon, nakakita na tayo ng dalawang sets na ang measure nila ay 0. Lahat ng finite set, ang measure niya ay 0. Lahat ng countable set, ang kanyang measure ay 0. Ang measure ng isang interval ay yung length niya. So ang isang interval, hindi na siya measure 0. Kasi ang measure ng isang interval ay yung haba ng interval na yon. Okay? More on measure, yung konsepto ng measure ay dinidiscuss siya sa Math 230, which is the graduate level analysis course. Yun yung measure theory na tinatawag. Magde-develop tayo ng paraan ng pagsusukat sa mga functions, sa mga sets, and so on. Pero ito lang naman yung kailangan natin, yung pagiging measure 0. Kasi kailangan ko siya para sa Lebesgue's criterion for Riemann integrability. And we will end here. Banggitin ko na lang siya. Ang sinasabi ni Lebesgue, kapag meron kang isang function f na bounded sa isang closed interval AB, then si f ay Riemann integrable if and only if the points of f, where the points where f is not continuous, has measure 0. Okay, so ibig sabihin, pag bounded, as long as bounded yung set mo, tapos measure 0 lang yung points kung saan siya discontinuous, then siya ay Riemann integrable pa rin. Pag hindi na measure 0 yung set kung saan siya discontinuous, then hindi na siya integrable. So kanina yung example natin, yung isang theorem natin, well, we know that the z-subice being finite will have measure 0. So ibig sabihin, ito ay special case lamang ng Lebesgue criterion. Okay? Tapos, nasabi natin na, itong floor function, discontinuous siya sa closed interval AB kasi discontinuous siya sa mga integers na nasa closed interval AB. Pero finite lang naman yung number ng mga ng mga integers sa closed interval AB. So measure 0 din yon. So ito ay integrable pa rin. Kaya lang si Dirichlet function, yung 1 kapag ka si x ay rational, tapos 0 kapag ka si x ay irrational, ito ay discontinuous sa buong interval 0, 1. Alright? Dahil discontinuous siya sa closed interval 0, 1, ang measure ng closed interval 0, 1 ay 1. So, si Dirichlet function ay discontinuous sa isang set na ang measure ay 1. So, by Lebesgue's criterion, hindi na siya integrable. Kasi sabi ni Lebesgue, integrable siya if and only if dapat yung points of discontinuity niya has measure 0. But the Dirichlet function being discontinuous on the entire closed interval 0, 1, which turns out to have measure 1, then the Dirichlet function is not Riemann integrable. Kasi itong Lebesgue criterion ay if and only if. All right? And I think that's a good time to stop today. Parang naparami yata yung diniscuss ko today. Medyo komplikado kasi yung mga proofs. But I hope you got something from today. Don't worry, I will not ask you to prove Lebesgue's criterion. So, pakitandaan lang. Kapag measure 0 yung points of discontinuity, then Riemann integrable ka pa rin. Pero pag hindi na siya measure 0, hindi ka na Riemann integrable. Okay? So next meeting, we will address the question of how to actually compute for the integral of f over the interval AB. Kasi laging criteria lamang para maging integrable. So next time, we'll look at paano mag-compute ng Riemann integrability or ano yung mga techniques para computein yung Riemann integral ng isang function. And segue tayo after that para tingnan ano yung mga properties ng Riemann integral. Okay? So I'll stop here. Do you guys have any questions, clarifications, concerns? Okay? So kung wala na guys, all right. Extended hanggang bukas yung ating homework number 6. I'm thinking kung magbibigay ako ng homework 7, pero antayin niyo na lang yung announcement ko sa Canvas, okay? Absorbing pa rin. That's fine, Michael. At least ngayon siguro napag-usapan natin to, and then habang kung meron kayong tanong later, pwede nyo akong i-chat, ano? Or you can rewatch the recording if something is not clear, ano? Or kung gusto nyo balikan. All right, so we'll continue on Tuesday. But until then, guys, keep safe and enjoy the weekend. Bye-bye.
Thank you po, sir.
All right, you're welcome. Uy, bumalik pa si Prince. Bye-bye na, Prince.